series. But before we talk about that, we will finish up our last slide in 8.5. 8.5, and then we jump to 8.9. Okay, so here's our last problem with PFD, or, well, let's see. Okay, so we're going to find a volume. We are rotating this around the x-axis. And we've got, this is a graph I would never expect you to be able to graph on a test. You wouldn't have, I would give it to you if this was a curve that you were going to do something with. I would not expect you to be able to graph that. So we're going to rotate around the x-axis. And what technique should we use? Disk, washer, or shell?
Shell.
Disk. Because this is our axis of rotation. And the natural choice for our element is vertical, because we have an upper curve right here and a lower curve there. If we try to draw a horizontal element and we're thinking about right here, we'd be bonking right into that. So that would not be the optimal way to draw your element. We want to draw it as a vertical element. And if the element and the axis are perpendicular, you have a disk or a washer. Because the element is touching the axis, you have a disk and not a washer. So we will build a disk, and pi r squared is the area of a disk. So the area, generic formula, pi times the radius squared. And what is the radius in this case? Function. Yeah, the function, 1 over the square root. Yeah, I could not hear you. So I'll assume that's what you said. Let's go. So we are going to square that function. That'll be our disk area. So that's measuring the area of the disk at x. We can obviously simplify that pretty easily. So we will end up with pi over 4 minus x squared. And it might not have been obvious at first that we would have to use PFD, but it should start getting obvious. Because PFD, what is the primary need for our integrand in order to use PFD? What has to be true about the denominator?
Factorable.
The denominator has to be factorable. So if the denominator is factorable, that makes partial fraction decomposition a possibility. If it's not factorable, we definitely would not even consider PFD. Okay, so volume, we'll factor the pi out to the front. Is there symmetry that we could use here so that we can have limits of integration with like a 0? Yeah, so we'll go 0 to 1 instead of negative 1 to 1. So we're going to put a 2 out in front. So that's a symmetry 2. Symmetry. Yeah, this classroom is way hotter. So 2 pi and then integral 0 to 1 instead of negative 1 to 1. And we look at this denominator, 4 minus x squared. And to use PFD, we have to factor. And we could factor that difference of squares as it is. Usually, we like it to be x squared minus 4 and have a decreasing order with the x's, usually. It really doesn't matter. In this case, it's going to be just fine not to do that. So let's just do it that way then. So we'll leave it as it is, just for the heck of it. If you wanted to write it in descending order, you could write it as negative x squared plus 4. You could factor out the negative 1 then, and you'd have x squared minus 4 with a minus on the outside. But we'll just do it this way. We'll do it in this slightly different way. So we're going to take our integrand, and we're going to write it as a divided by b plus, a divided by 2 minus x, and b divided by 2 plus x. So that'll be our PFD.
What about 2 and negative 2?
Say that again?
A and B, 2 and negative 2.
That's what they're going to be equal to? All right, let's find out. So So we're going to multiply both sides. Oh, that's convenient values.
Yeah.
Yeah, convenient values will be that. Yeah. So multiply both sides by the denominator. So let's get to this point first, and then we'll plug in our convenient values. And the convenient values are -2 and 2. Any issues yet? Convenient values? Makes sense? Convenient values are the values that cause the factor to be 0. So 2 plus x is 0 when x is -2, so that's a convenient value. And this other factor is 0 when x is 2, so that's a convenient value. And when we plug in these convenient values, we plug -2 for all the x's that we see. Plugging in -2 here makes this whole term go away. Plugging in -2 right there, that's going to make that a 4b. So b will be a 4th. Similarly, when we plug in 2 for all the x's that we see, that term on the right is going to vanish, going to turn to 0. And that'll be a 4a. So a is positive 1/4 also. All right, how about up to that point? Finding our coefficients. Any questions on that? Finding coefficients? All good? Yep.
Well, how would we do it if it was like the other method?
The traditional method?
Yeah.
So if we were going to do traditional method, we would multiply this all out. So we would have ax minus bx, and a minus b would be 0 because there's no x over here. And then the constant would be 2a plus 2b equals 1. Does that make sense?
Yeah. I think that was like the thing I was having most trouble on like the homework. So
Uh-huh.
we like run through.
Yeah, we can write that out. Easy. So this is the convenient value method, and if we wanted to do the traditional method, which is the method that we want to do if we have a nonlinear, so most of the time we wouldn't do it here, but it's absolutely going to work. So the first thing we do is multiply this all the way out. We expand it. And then on the left-hand side, we can put a placeholder here and think of this as 0x. So with the traditional method, we want to match the corresponding coefficients. Coefficients of x have to be the same. The constants have to be the same. And so when we look on the left, the coefficient of x is 0. And on the right, the coefficient of x is a minus b. So that'll be our coefficient of x on the right. So we're taking the coefficient here, and we're matching it with those two coefficients. And then with 1, that's the constant on the left. That's got to match the constants on the right. The constants on the right are 2a and 2b. So it'll be 2a plus 2b. And so here, again, you can use substitution or elimination. It does not matter. Let's just do substitution this time. This tells us that a is equal to b. And so if a is equal to b, we could rewrite this as 1 equals 2b plus 2b. So 1 will be 4b, so b will be 1/4. And if b is 1/4 and a and b are equal, then a is also going to be 1/4. So we'll get to the same point. So either method will work, especially with linears.
Will you care which method we use on the exam?
No. Yeah, it's totally up to you. If you feel better with one than the other, totally fine. Or if you want to use a hybrid method, you can. Some people like the hybrid method. Okay, so that tells us then that we can rewrite, I think we can squeeze it in up here. So we're going to rewrite our integral as 1/4 and 1/4. So let's factor that 1/4 out to the front, actually. Let's factor that 1/4 all the way out to the front. So we have 2 pi divided by 4. That'll be our coefficient, 0 to 1. And we are going to have 1 over 2 minus x and 1 over 2 plus x. All right, so now we have to integrate those two. They both are logs, but we have to be a little careful because the first one has a negative sign down there. So here's a safe way to do it. Let's break it into two integrals. And what do we want our numerator to be for this integral?
-1.
-1. So if we put a -1 there, we have to put a negative in front. And then this second integral is already in log form. Let's just integrate at the same time, though. So let's just pause for a minute here. We'll just leave it. So we have that. So the integral of this first one then is going to be what?
Negative natural log of x.
Natural log of 2 minus
Yeah,
x.
2 minus x.
Whatever the denominator is, we match that denominator. So when the numerator is exactly the denominator, it's derivative, we just take natural log of the denominator. And then over here, it's in log form. And then this went from 0 to 1. A little more space. So plugging in 1 is going to give us right there, if we plug in a 1, 2 minus 1 is 1. Natural log of 1 is
2.
natural log of 1 is 0. Natural log of 1 is 0. Right? The natural log function looks like that. There's 1. So that term is going to be 0. And then we end up with natural log of 3, plugging in 1. And now we have to subtract off the antiderivative at 0. So we plug in 0 here, we get natural log of 2. And we're subtracting those, so it's minus a minus, so it's plus natural log of 2. And then again, we're subtracting here, so then it's going to be minus natural log of 2. So we're going to end up with pi times natural log of 3 over 2. That'll be our volume.
I just want to look back at the traditional method, and I want to see how she solved it from there. You get 0, and
So this one are the yellows, and this one is the greens.
then you did, how'd you get A equals B?
Adding b to both sides of this equation. Add b over,
Oh, okay.
and then plug it into the second equation. Plug in a b right there, and then solve for b first, and then back substitute to get to a. Any part of the integral steps that you're not sure about?
I was wondering, so that 4 there and the 2 pi over 4, that came from the 1/4.
Exactly. So
Okay.
the a and the b are both equal to 1/4. So those are in the numerator right here, and you can just factor that out to the front because they both have that same numerator of 1/4.
Okay.
So we can factor that right out to the front.
And then remind me why you made that 1 over 2 minus x negative?
Yes. So this, to put it in log form, we want the denominator's derivative to be in the numerator.
And x is negative. Okay.
Yeah. The derivative of 2 minus x is -1, so that's what we want in the numerator. And then we have to offset it.
Thank you.
Yeah, sure. And then if it's in that log form, then it's just natural log of the absolute value of the denominator. Okay, so that's the end of 8.5. I guess it's 8.5, not 8. It's 8.5. So now our only other section that we're doing is 8.9. So,
What about chapter 9?
well, we'll do chapter 9 next time. Yeah, chapter 9, we're only doing 2 sections, 9.1 and 9.3. So we will do our review a week from today.
What?
You don't have to review if you don't want.
We're doing 9.2 and 9.3 at the same day?
9.1 and 9.3.
9.1 and
Wait.
9.3 on the same day?
Uh-huh. They're very
Today's
tiny.
Wednesday.
They're very tiny. 9.1 and 9.3 will take us less than 1 period.
Cool.
It's just an introduction to differential equations.
So we're not actually doing that.
Okay.
Not really.
Thank God.
Yeah, we're doing the most basic differential equation thing. Okay, so before, let's see, do I want to even bring this slide up? Not yet. So let me ask you a random question, because this is the underpinning for all of 8.9 and infinite series. Basic question. This is the thing that should be in your mind every time you see an infinite series or you see an improper integral. Basic concept. Can you add an infinite number of positive values and get a finite answer? Infinite number of positive numbers. Can it be finite?
Yeah.
Can you say
Give me
that?
an example if you think it can be yes.
What was that question again?
Can you add an infinite number of positive values and get a finite answer?
Wouldn't anything with an asymptote be that example?
That's not a number. I said an infinite number of positive numbers.
I don't know specifically off the top of my head.
Somebody have an example?
The odds? All the odds?
Add all the odds and you're going to get a positive finite value?
Probably.
Finite.
None of this negative pi over 12 stuff. None of that stuff.
But the
That would
video.
be-
Gerardo, can you do it?
You tell me.
Yes, sir.
Let's try.
Let's try. Okay, so what if is 0.3 positive?
Yeah.
Depends on how you route.
Is 0.03 positive?
Yes.
And you know where we're going already, right?
Limit.
Okay.
These terms, what you just said is super vital. These terms are all getting closer and closer to 0. This is an infinite sum of positive numbers that has a finite value. Right? We know that that finite value is 1/3. So that is what the underlying concept is with improper integration and with infinite series once we get to infinite series in the coming chapters. So it's very tempting to think that when you're adding an infinite number of positive values together that it must just, like be a balloon and explode eventually and go to infinity. But if the values are going to 0, it's possible that the sum is finite. Now here's another example where the terms are going to 0, but this sum will not be finite. So here we have a similar situation. These terms are definitely going to 0, but that infinite sum is going to be infinite. It's not going to be finite. So the whole point in chapter 8.9 and in chapter 10 and 11 is to figure out, okay, these terms are going to 0, these terms are going to 0, but they're not going to 0 fast enough. That's the problem. So that's what 8.9 is. Primary idea is, okay, well, what does it mean to be going to 0 fast enough? You can think of these as areas of rectangles. And that's what we're going to be doing here. Our goal with improper integration is to figure out if this collection, this sum of an infinite number of positive rectangular areas is finite or not. That's what improper integration is. Improper integration, you will know that you are dealing with improper integration if you are trying to find the area of an unbounded region. So that region that we're trying to find the area of goes on forever. So it's unbounded. seems like the area should be infinite, but we now know it could not, it might not be infinite. Because if these are representing the areas of rectangles, you can have an infinite number of rectangles that add to a finite value. They just have to be going to 0 really quickly. So that's what we're going to do, is try to figure out when they're going to 0 quickly enough. So here's the strategy. We can either have our unbounded region be horizontal tails. So visually we see a horizontal tail that's going off forever, right? Going off forever. So unbounded region. You could also have, it's on the next slide, or a couple slides down, you could have a vertical unbounded tail also. Could be horizontal or vertical. The vertical ones are a little more complicated because you are not going to see infinity in the limit. When you see infinity in the limit, it's an improper integral. You know instantly. You don't even have to think about it. If you see infinity, it's automatically improper. You're automatically dealing with an unbounded region. So if we see infinity, these are the easier ones to deal with because we see the infinity right in front of us. Then we know it's improper. And our strategy is to say, hey, let's chop it off right here. Let's chop it off at b. Let's find a definite integral. So if we integrate from a to b, this is now a definite integral. And then we're going to take the limit. It's basically the limit of a Riemann sum. So that sum of rectangles right here for the definite integral is going to give us a function. And then we take the limit of that function. That's going to be our strategy. Limit of a Riemann sum.
Do you pick B to be like an easy place to take an integral or something?
B is just going to be a letter. We're not even picking it. It's because we're going to let it go to infinity. So it's kind of like the disk and the washer thing where we found the area of a disk or the area of a washer or the area of a cylinder, and that was a general function. So it was the disk at x. So if we plugged in a different x, we get a different area. Okay. Same idea here. If we plug in a different b, we'll get a different definite value. But we won't ever pick the b. We're just going to let the b go to infinity. So what you're going to see then is that this area here is going to end up being a function of b right there. We are going to know what a is. They're going to tell us where to start. But that'll be a function of b. If we have a definite integral with a letter, you always end up with a function. You don't end up with a constant. A definite integral with two numbers gives you a constant every single time. But if we have a letter, we're going to end up with a function of that letter. Okay, so this book puts the interval, they always do the interval in this book as a on the left, b on the right. If our tail is to the right, we're going to let b go to infinity. If the tail is on the left, we're going to let a go to negative infinity. But do the same thing. And if we have a double tail, you cannot, it's tempting to say, let's just integrate from negative a to a and let a go to infinity, but you cannot do that. What you have to do is break it apart. And here you can break it apart somewhere convenient. Typically we break it apart at 0. But it doesn't matter. So what we're going to do is think about this as two different improper integrals. So we're going to have the improper integral on the left and the improper integral on the right. And this double-tailed improper integral will converge. If you get a number, we call it convergent. If you get infinity, you call it divergent. So if the area is finite, we call it convergent. And we will have a finite area for the double if both of the singles are finite. If one of the tails is infinite and one of the tails is finite, the sum will be infinite. So the only way to get finite is if both are finite. Both have to be constants. Okay, so we're going to call these horizontal tails, we're saying that they're horizontally unbounded. Horizontally unbounded. You can go forever and you never get to the end of the region. It'd be a hard region to paint. Okay. So let's look at this first one. So here, they're conceptually showing us that, hey, let's just imagine the B is right there. So if we imagine the B is right there, we're just imagining all these rectangles right up to the B. But then if we let the B creep out to the right a little bit, then we're adding some more rectangles and we're getting closer to the true area. So conceptually, that's what we're thinking about, just making this definite integral creep out further and further and further and further, and then we let B go to infinity. And if we get a finite result, the area is finite. If we get infinity, the area is infinite. So here is our first one. So we're integrating from 1 to infinity, 1 over x squared dx. And I think you all agree that that has a limit of 0, 1 over x squared. So that curve is approaching the x-axis. So kind of the question is it approaching the x-axis fast enough?
Looks like it.
It certainly looks like it. Certainly looks like it's approaching very fast. Looks like the white slide at Waterworld. So that can't happen for a couple months, but
You can try.
we could try. Let's go climb over the fence at Waterworld.
What if we slow down it so fast we generate it?
Take the short range button.
All right, so there is what we're going to integrate.
So your problem would originally start out with like integral of infinity to 1, right?
1 to infinity.
And then from there you would convert infinity into b.
Yes.
Okay.
Yeah, that's right. So as soon as we see that infinity in the limit, we know right away, as soon as we see that, the next word that we write is limit. Because we turn this into the limit of a definite integral. So this right here is definite. So we take the limit of a definite integral. That's what we always will do.
Now, whether the infinity is on the top or bottom, does that tell us where either we're going left or right?
Yes.
Okay.
So if we have plus infinity on the top, that means that we are integrating, yeah, the tail is to the right. So if it's going from negative infinity, that means the tail will be on the left. If negative infinity was at the bottom. And then we integrate. So we get x to the negative 1 over negative 1, which is this. Negative 1 over x. So that limit symbol is just hanging out while we do our regular definite integral business. So we're just letting the limit hang out. Plug in the b, plug in the 1. So there is our definite integral. This tells us the area from 1 up to whatever you chose for b. If you chose b to be 2, then this area up to 2 would be 1/2. If you choose b to be 10, then you're finding the area between 1 and 10, and that would be 9/10. So that is giving us snapshots of what the area is as we go further and further out.
The limit's still going b to infinity.
b
right?
goes to infinity.
Okay.
And you don't have to rewrite it every single time. If you want, once you've established it once, like right there, you don't have to keep rewriting. Some of these things are going to have like 8 lines, and you don't need to write b goes to infinity 8 times. You have to write the limit word, though, so we know it's the limit. And what does 1 over b go to as b goes to infinity?
I mean, zero.
Someone other than Ryan?
Yeah.
0? Negative 1? What is
I saw the negative 1 up there.
Just because you see a number doesn't mean.
That's what physics says.
Oh, yeah. So that is the area. It's kind of funny. You see this curve approaching the x-axis. Even if someone told you the area was finite, you would probably not suspect that it was an integer, right? We're so used to like finding things like, you know, irrational numbers, some multiple of pi, multiple of square root of 2. So that area is exactly 1 unit, 1 square unit. Okay? So keep this in our head. 1 over x squared converges. So 1 over x squared, if the power is a 2 in the denominator, that's fast enough to give us convergence. 1 over x squared converges. All right, another. All right, so here is another function. This is an exponential function. It's exponential decay. And if we look at the Desmos graph, it certainly looks like it's approaching the x-axis really fast. And if we think about what we know with regard to exponential functions, we know that they decrease really fast or increase really fast. Now, when someone says something's growing exponentially or decaying exponentially, generally we're thinking of it going fast. So intuitively, we're probably suspecting that this is going to be a finite area down here. Well, let's find out. The second we see that infinity right there, we know it's improper. We know it's an infinite, it's an unbounded tail. We know we have to write the word limit, very next step. Limit. And b will go to infinity. Integral from 1 to b, 2 to the negative x dx. So we're integrating an exponential function with base 2, not base e. So the antiderivative for an exponential function is always itself. That's where we start. Integral of an exponential starts with itself. And then we do the reverse chain rule. So what are we going to have to divide by? Negative 1, which we just put that out in front. And then something has to happen with that too. It's not an e. Anyone remember what we do when we're integrating?
Log?
Divide by log of the base. Yeah. So when you're integrating a non-natural log or a non-natural exponential, you have to do this extra correction and divide by the natural log of the base.
Why is it natural log and not LOG?
Why is it? Say that again?
Why is it natural log and not LOG?
So do you remember what the derivative of 2 to the x is?
No.
Do you remember how to do it? 2 to the x? What's the derivative? 2 to the x, natural log of 2 times 2 to the x, yeah. How did you do that? So remember back in Calc 1, you had a technique called log differentiation. You took the natural log of both sides, and taking the natural log of the right side allows you to pull the exponent down. And now we're going to differentiate both sides of this equation. What is the derivative of natural log of y? 1 over y times the derivative of the inside. The derivative of the inside we call y prime. What's the derivative on the right side? Nope. What's the derivative of 5x?
5.
What's the derivative of natural log of 2 times x? Natural log of 2. Right, that's just a constant times x. And so then we isolate the y prime, and we get y times natural log of 2, and we look back up, and y was equal to 2 to the x. So that's why we use natural log, because that's what happens with log differentiation. So yeah, so there we have it. And if we wanted to, if you wanted to integrate, if you want to integrate both sides here, well, this would be doing a little differential equations. You have no fear. You have no fear.
I'm afraid.
I'm scared.
Don't be afraid. Okay, so if we wanted to integrate, say, the 2 to the x piece, here's what we're going to do. We're going to just get the 2 to the x piece all by itself over here with the dx. So this is what we're going to do on Monday. So this is called separation of variables. We put the y's on the left, the x's on the right. And what you can do is integrate one side with respect to y and one side with respect to x. And so the integral of 2 to the x is going to be equal to, over here, the integral of y, the integral of dy is just y. So we're going to get y over natural log of 2 equals the integral of 2 to the x. And then we go back and substitute what y was equal to. Y was equal to 2 to the x. So we get 2 to the x divided by natural log of 2. And we will have to put a constant of integration in there. So let's just slide that over and put a plus c just to be complete. And everybody see that y is equal to 2 to the x, so that's going to go right in there. So the integral of 2 to the x is going to be 2 to the x over natural log of 2. So if you're integrating, you divide by natural log of 2. If you're differentiating, you multiply by natural log of 2. Very similar to chain rule and reverse chain rule. Chain rule, you multiply by the derivative of the inside. Reverse chain rule, you divide by the derivative of the inside. So same process. Multiply for derivative and divide for integrals. All right, so let's get back to calculus 2. So we just let the limit symbol hang out here, and now we evaluate the antiderivative with b. So we're going to have the negative 2 to the negative b. Now here's where you have a couple of choices. It can get really kind of messy in here. One suggestion is to factor out the constants before plugging in those limits of integration so that the limit is as simple as possible and it's not all cluttered. I think that's a good strategy. So why don't we pull out the constant? So let's take a look here. The constant, we have a negative 1 over natural log of 2. Let's get that out in front. And then we have limit. So now we're only focusing on that 2 to the negative x. That's going to be just a little cleaner. So 2 to the negative b is 1 over 2 to the b, minus, plugging in a 1 up there, is going to be 2 to the negative 1, which is 1/2. And brackets or parentheses, whatever fits. So this constant right here, we pulled to the front. So this is all out in front. So the only thing left is 2 to the negative x. So 2 to the negative b minus 2 to the negative 1. And now we're ready to take the limit. So this limit is as b goes to infinity, and what is that equal to? Negative 1/2, because 1 over 2 to the b is going to go to 0. If you have a constant in the numerator, and the denominator is going to infinity, those fraction values are compressing to 0. If the numerator is constant and the denominator keeps growing, fractions are going to 0. Everyone agree with that? So it's like 1/10, 100th, 1,000th, 1,000,000th, right? Those are going to 0. So we end up with negative 1 divided by natural log of 2 multiplied by negative 1/2. So our final answer is 1 over 2 natural log of 2. All right, so finite also. Finite also. So the exponential decay function is going to the x-axis fast enough. 1 over x squared is going to the x-axis fast enough. Any questions in the integration? Yeah?
Not in the integration, but like, so what does the answer mean? Like,
What is it what?
Like, what does it mean?
It means that that's what this area is. So whatever that number is, if you wanted to round it to a decimal, that is the square units that make up this area.
Oh, I see.
So let's just say it's 0.8. Then this area right here is 0.8 square inches, meters, whatever. Yeah.
So that infinitely approaches x and never touches x. And that-
Never touches x, horizontal
that area
asymptote.
is finite?
And the area is finite. Yeah. This is where we start to get into abstractions.
No.
Can you just review one more time that ln2 -2 situation, if they're the green highlighted?
So are you okay going from here to here?
Not quite.
Okay, so if we are integrating a log function, excuse me, an exponential function that has a bit, let's just get rid of the minuses. If we have something like that, if we're integrating an exponential that has a non-natural base, then the integral of an exponential, we always start by doing itself, no matter what. And then we divide by the natural log of the base. So if this was a little more complicated, if it was 5 to say the 3x minus 1 dx, same thing at first, we rewrite the whole exponential function. We first do reverse chain rule. Reverse chain rule says take the derivative of the exponent and divide by the derivative of the exponent.
So how do you know to use this one over the 1 over a e to the ax? Isn't this like pretty similar? There's a formula that's the integral of e to the ax.
So that has a natural base though.
Right, it totally does. Yep.
Right, so this is going to be the exponential itself, but then the reverse chain rule does the division by a.
Yep, that makes sense.
And so then what's the last step here then? Divide by natural log of 5. Divide by the natural log of the base. So if it's a non-natural exponential itself, divide by whatever the RCR thing is, and then divide by natural log of the base.
With e to the x, the same thing's happening, right? But it's natural log of e is 1, so then you never write it.
Exactly.
Okay.
Right? So if it's a natural exponential, you have e to the 2x. It is itself divided by the 2 divided by natural log of e, but natural log of e is 1. Yeah. That's right. Dan?
I had a question about convergence. So if we know 1 over x squared is going quickly enough, can we then infer that 1 over x cubed, 1 over x to the 4th all will then be convergent?
So great question. So he says if we've shown that 1 over x squared is fast enough, 1 over x cubed and 1 over x to the 4th and 1 over x to the 5th, they're going to be even faster. Right? Those fractions are going to go to 0 even faster if the exponent is bigger than 2 in the denominator. So that is right.
1 over x.
That's not, that's going the other direction. So the direction you're talking about, 100%. If we make that exponent bigger in the denominator, and the question's going to be more interesting if we make it smaller, make it closer to 1. That's going to be the harder part.
If they go to 0 faster, does their area
It's
get
smaller. Yeah.
Yeah.
Yeah, so if we looked here, so the prior one that we did, 1 over x squared, we did the area from 1 to infinity. So this one, the exponential is going to go to 0 even faster than 1 over x squared. So if we did the area from 1 to infinity here, it would be smaller than the 1 over x squared. That's right.
Is it possible to get an area of 0?
No.
Doing this or no? Okay.
No. You cannot have an area of 0. If you have a curve that's above the x-axis, there is positive area. Right. So here's one going the other way. We have a left tail. So once again, we see it just jumps right out at us. We see the negative infinity. So we know instantaneously that we have an improper integral. We know instantaneously that the next word we write down is limit. And a will go to negative infinity.
Why are we doing a now?
Because it's the left endpoint that's going to. And then we pop the denominator into the numerator.
Is that a plus infinity?
A goes to infinity. Arrow.
Arrow.
Arrow. And then this we can integrate power rule and reverse chain rule. So we're going to have limit of, so we're going to add 1 to the exponent. So adding 1 to negative 1/3 gives positive 2/3. Dividing by 2/3 gives multiplication by 3/2. And then what about RCR? Divide by negative 1. So we'll put that negative 1 right there in front of the 3. And this will go from a to 0. let's write it down here. So we're going to have limit as a goes to negative infinity. Let's pull out that negative 3/2. Let's get that out of the way. Always easier to evaluate limits when the extraneous constants are out of the way. So plugging in 0 is going to give 2 to the 2/3. That's a constant. The limit of a constant is itself. Minus quantity 2 minus a to the 2/3. Now we have to evaluate that limit. Now looking at the Desmos graph gives us a hint. This curve does not look like it's approaching the x-axis very fast. What is the power on the x in the denominator here?
2/3.
3/2. No. Sorry. What is it? 1/3. 1/3. I heard all sorts of things in my head. Everyone agree that's a 1/3 power on the x?
Yes.
That's a 1/3 power on the x.
Yeah.
Third root is a 1/3 power. So that power is smaller than 1, which means the fractions are going to go to 0 even slower than x squared or other ones. So we're going to suspect that this diverges. Right? Okay, so when we're evaluating improper integrals, 90-something% of the time, you should just be confirming what you suspect. So it's all going to be about looking at the power in the denominator. If the power is bigger than, we're going to see if it's bigger than 1, they're going to go to 0 fast enough horizontally. And if the power is less than 1, they're not going to go to 0 fast enough. So it really is going to mean about confirming what we suspect. So let's see if we suspect that it's going to be infinite. Let's see. Now usually with these, you want to start on the inside and go out. So come all the way in here. If a is going to go to negative infinity, where is 2 minus a going to go? Positive infinity.
Yeah.
Right? 2 minus infinity. It's going to go to positive infinity. And then if you take something that's going to infinity and you raise it to a power, still going to go to infinity. So this whole thing is, with the 2/3 included, is still going to positive infinity. And then what about a constant minus infinity is negative infinity. And then negative infinity multiplied by negative 3/2.
If we wrote 3 infinity over 2 infinity, how would you feel?
Angry. All right, so that's going to be infinite. And so what we say here is that the integral diverges. So therefore, we have a divergent integral. Therefore, diverges. Yeah?
So 2 minus a was just replaced with infinity because the 2 doesn't matter at that point?
So, well, we're thinking to ourselves, 2 minus infinity, which is 2 plus infinity. And so the 2 doesn't matter when you're adding it to infinity. It's still infinite. And then if you look at a fractional exponent, anytime we have a fractional exponent, the picture in your mind should be the bird wing. Fractional exponent in quadrant 1 is going to look like that. As it grows slowly, but it does go to infinity. Right? Any fractional exponent, truly fractional. 1/3, 2/3, 4/5, 9/10, 11/13. If that exponent is a fraction, you always have this in quadrant 1. It goes to infinity. There's no horizontal asymptote. Okay, so that one diverges.
We did 1 over x.
Okay. Double tail. So if we have a double tail, this is really 2 problems built into 1. We have to separate it somewhere, and it doesn't matter where. But what's the obvious place to separate it? 0. Wait, what? Okay, so so if you're looking at the high point, that's a reasonable place. But isn't it easier to evaluate limits when you have a 0 as one of the limits of integration?
Yeah, sure.
Shad, were you joking on me here?
No.
Okay, so we want to break it apart at 0 just because it's easier to evaluate when you're plugging in 0.
Can we do a partial fractions?
You can do whatever you want. Whatever you want. If it works. So we're going to treat this as a limit as a goes to negative infinity of a to 0 dx over x squared plus 2x plus 5 plus limit as b goes to infinity, same exact integrand. A to 0 and then 0 to b. All right, so there is our setup. So we have two improper integrals. So we broke it apart at 0. We're going to find the right tail area, the left tail area, and add them together. In both cases, the integrand is the same. So why don't we go off to the side and figure out what the antiderivative is for that? Ryan, you can use partial fraction decomposition. The rest of us won't. If you are so inclined to try to factor this, I would love to see it. So do you notice that there's that's not factorable? So we have to complete the square. If it's not factorable, complete the square. So we're going to have x squared plus 2x plus 1 plus 4. So we'll have that. So hopefully you're dreaming of inverse tangents. So when we complete the square, we see that we have a sum of squares in the denominator. We would like it to be a sum of squares with a 1, because that's going to make life a lot easier. So that's what we get when we factor out the 4. When the 4 comes out, there is no 4 here, so you can imagine multiplying that by 4 over 4 and factoring out that 4. And then you rewrite this so that it's a single quantity that's squared.
Now can we do? Yeah.
And now we can do inverse tangent. So this will be 1/4. I'm going to leave space for RCR. Inverse tangent of whatever's in the parentheses plus c. And what's going to go into that little RCR gap?
2.
So the derivative of x plus 1 over 2 is 1/2. Dividing by 1/2 means multiplying by 2. If, when you look at x plus 1 over 2 and it's not totally obvious to you what the derivative is, if you need to, write it out. So write it out as a linear expression. All this RCR stuff is always for a linear expression. Always. RCR is always linear. So your derivative will always be a constant every single time. Dividing by 1/2 gives that. And then we're just going to simplify this a little bit. Make that a 1/2 out in front. All right, so now we have our antiderivative. So let's pop back up here. So 1/2 arctangent of x plus 1 over 2. So 1/2 arctangent of x plus 1 over 2. This is going to go from a to 0 plus the limit of 1/2 arctangent x plus 1 over 2. 0 to b. Now we are ready to plug in our limits of integration.
Where did we go?
Where did we go? What do you mean, where did we go?
I'm jumping around the page. What was forward?
We're just going back up. We found our antiderivative right there. Now we're gonna, there's our antiderivative, so now we're putting in our antiderivative for these two integrals. Okay, so the 1/2, let's pull that out to the front. So 1/2 limit, and this one is as a goes to negative infinity. And then we're going to have arctangent of 1/2 minus arctangent of a plus 1 over 2. Plus 1/2 limit as b goes to infinity. The other thing. So we're plugging in the upper and lower limit. Everyone okay with this? The upper limit is 0. Plug in 0 right there, and then plug in a. Same thing here. The 1/2 to the front, plug in the b, so we get arctan b plus 1 over 2 minus arctan of 1/2. So that's where we're at. Let's draw a picture of arctangent just because we need to be super clear on arctangent. So arctangent, let's put this graph here to remind you what it looks like. So arctangent is one of the few functions that you encounter that have two horizontal asymptotes. This horizontal asymptote is at pi over 2, so y equals pi over 2. This horizontal asymptote is at y equals negative pi over 2. So that picture needs to be in your mind, because you are going to see inverse tangent a lot. So that gives us a clue. As a goes to negative infinity, where does this go? Inverse tangent of negative infinity. So forget about the minus there. Just look at the inverse tangent. If a is going to go to negative infinity, that means the inside of inverse tangent is going to negative infinity. The inverse tangent values are going to negative pi over 2. So that's going to go to negative pi over 2. Over here, if we look at this inverse tangent here, now b is going to infinity, which means the inside of arctan is going to infinity. So if the inside of arctan is going to infinity, the y values are going to pi over 2. Okay, so limits of inverse tangent. What are we left with? So we have 1/2. Arctan of 1/2 is a constant.
Yes.
So we just leave it. It's constant. And actually, let's just go ahead and distribute this 1/2 business here. So it's 1/2 times arctan of 1/2 minus 1/2 multiplied by negative. So this 1/2 is coming in, negative 1/2, and then we have negative pi over 2. Plus 1/2 multiplied by pi over 2 minus 1/2 multiplied by inverse tangent of 1/2. So we get pi over 2.
All that.
All that.
Wow.
Right? Very satisfying. So half arctan minus half arctan, those cancel.
Oh, wow.
Pi over 4 plus pi over 4 is 2 pi over 4, which is pi over 2. Look at that.
My back.
That is not a buzzkill.
That is a buzzkill.
No, no, no. That is a very fine answer. It's a little irrational. Okay, let's go ahead and take a break. If you have any questions, we flying. Flying right into a window.
Well, the arc tangent goes to infinity. Goes to pi.
Yes.
I didn't change it. You didn't change it. Well, it's
Okay, so let's go through the U sub if you haven't already gotten through it already. When you're thinking about U sub, remember that whatever you let U be equal to, the derivative has to be in the integrand. So there's really only two choices here. U equals the denominator or the numerator. And if you let U be the denominator, its derivative is 2x, and there's no 2x. So really, the only candidate for U sub is arctangent. And there's the derivative. And we see the derivative in the integrand, so we are moving in the right direction. So is that just U to U? U to U? So U to U. Now these limits are U limits, and we're going to just go back to X, so I'll put placeholders. Converting limits with improper integrals is kind of a hassle. So we're going to have limit. We get U squared over 2. Back substitute. So we're going to get the limit of arc tangent squared times 1/2. Back to our original limits, 0 and b. Say again? Oh, 1. Oh, yeah, the way I was just looking at the graph. Yeah, let's go 1 to b. 1 to b. So this will give us 1/2 all the way out in front, limit arc tangent of b quantity squared minus arc tangent of 1 quantity squared. Arctan of b goes to, where does arctan of b go? Pi over 2, as b goes to infinity. So we will end up with 1/2 multiplied by, that's pi over 2 quantity squared, so that's pi squared over 4. And what's arctan of 1?
Pi over 4.
Pi over 4. And that's going to be squared, so we're going to get pi squared over 16.
That is a finite number.
That is a finite number. Multiply by 4 over 4. So we're going to get 3 pi squared over 8. No, that's not right. 3 pi squared over 32. What's that? All right, question.
Do another one?
Thank you, sir. Can I have another one? Everyone agree with the evaluation? Tan inverse of b, that's going to go to pi over 2. We square it. We get pi squared over 4. Arctan 1, that's the angle on the right with the tangent of 1. That's pi over 4. Common denominator, 16. All right. It's time to go to Gabriel's horn. Okay, Gabriel's horn. You guys know about Gabriel's horn?
Unlimited surface,
No.
surface area?
Finite volume, infinite surface area. Start to get to some of these weird abstract shapes. Finite volume, infinite surface area. So we're going to start with just the regular 1 over x curve right there. And that's going to be rotated around the x-axis. They call it Gabriel's horn. And let's first show that the volume is infinite. So the volume, we're going to rotate around the x-axis. So we imagine an element at x, and the radius is just the function. The radius is the function. Now, when we find surface area, we're going to have to differentiate the function. Because remember, surface area has that big square root of 1 plus derivative squared. So there's the derivative. OK, so let's focus on volume first. So here's volume right there. So pi, the radius is 1 over x. It's the function, squared. So we see it's improper, so we turn it to a limit, and we have this expression right there. So let's finish the volume. So this is going to be limit, add 1 to the exponent, divide by the new exponent. That's going to give us negative pi over x from 1 to b. The negative pi is a constant. Let's get it out of the way so we can take care of the limit. Oops, still need the word limit there. We have to put in the b and the 1. So this is going to be limit of 1 over b minus 1 as b goes to infinity. All right, and what does that limit equal? The 1 over b goes to?
0.
That goes to 0. So we're going to have negative 1. So we get negative 1 times negative pi, so positive pi. When all is said and done. When we combine our two signs, we'll get positive pi. So that is the volume of Gabriel's horn, pi cubic units. Pi cubic units. Now let's look at surface area. Unless you have a question on finding that volume. Any snags on the volume? Disk method, pi r squared. Okay, so surface area we're going to be a little, this is, not going to be on the exam. So let's just think about this. So for surface area, integral limits are still the same, 1 to infinity. 2 pi r h. So 2 pi r h. I said that wrong. 2 pi r ds. So it's circumference times ds. 2 pi r ds. I started to do a shell method. 2 pi r ds. So 2 pi, the radius is 1 over x, and remember ds from arc length is 1 plus y prime squared under a square root. So we get this. That is not integrable there's not going to be an easy antiderivative. It's definitely an improper integral, so we turn it over to a limit of a definite. And then notice this. So this number right here, do you agree that that number is always bigger than 1? You do?
I have a separate question.
Oh, separate question.
Can you move up a bit? Thank you.
So everyone agreed that that number is bigger than 1. Right? Bigger than 1. So that means that if you take this away, that's what this is over here, then this is going to be smaller. Think of it the other way, perhaps. If you think about this integral piece, there and there, that integral piece, if you multiply by something that's bigger than 1, doesn't it get bigger? Right? So if we have this, and we multiply by something that's bigger than 1, then it's bigger. Right? If you have 5 and you multiply by 3/2, you have a bigger number. If you multiply a quantity by something greater than 1, you end up with a bigger quantity. So this quantity here is bigger than that quantity because this quantity here is the same as that multiplied by a number that's bigger than 1. So we know for sure that our surface area is going to be bigger than the limit of this. And the limit of that is going to be infinite. Let's go through the steps. So right over here, we can factor out the 2 pi. And we're going to have limit of, what is the integral of 1 over x? Natural log of x. And our limits are 1 to b. So this is going to be 2 pi times limit. We're going to have natural log of b minus natural log of 1. Natural log of 1 is 0. So that's 0. And where does natural log of b go to as b goes to infinity? Infinity. Right? The natural log function, again, we know it looks like this. So natural log is going to go to infinity. So that tells us that this is infinite. So therefore, we have divergent. This is an integral that diverges. All right, so question.
So suppose that it didn't go to infinity and it was an infinite, how would you get back to the square root of 1 plus 1 over x to the 4th?
That's too complicated to talk about. Let's not talk about that. Yeah, so if it wasn't infinite, then we'd have to do some other work. Because then all we would know is that this integral here is bigger than that integral, which isn't that helpful. Here it's helpful because that's infinite, and bigger than infinite is infinite. So in that case, we'd have to do a lot more work. In that case, this argument wouldn't be a good way to go. Yeah, it's a good question. Okay, so here's the paradox. Here you get to think. Use your little gray matter. So if the volume is finite, you can fill Gabriel's horn with paint. It's finite. It's pi cubic units of paint. Fills it up. But if it's got an infinite surface area, it can't be painted. It's an infinite surface. But if it's filled with paint, it's painted. In fact, there's leftover paint. As you fill it with paint, the whole thing is painted. How do you resolve Gabriel's paradox? We'll talk about that next week. But think about it. Think about it. If it's finite volume, you can fill it with paint. Infinite surface, you can't paint it. But if it's filled with paint, it's painted. How do you resolve that paradox? Don't say anything. Think about it till Monday. Think about it to our non-snow class. Mondays. The non-snow days.
It's going to snow on Monday now that you said that.
Yeah, I hope not.
I hope so.
I hope it snows up there, not down here. Okay, here's another one. So we have this region, and we're going to find the volume and figure out whether this volume of this shape is going to be finite or infinite. Just looking at the graph, our suspicion is it's probably going to be infinite, because this is not going to the x-axis very quickly. All right. So, all right, you all write down the first couple steps. Write down the, so it's rotated around the x-axis. So write down that first integral that's going to represent the volume. At least get to the part where you write down the limit. Too many roots.
I gotta get better drawing straight lines.
Just use fractional exponents.
I don't like fractions.
Oh boy, then you're in trouble. I don't like fractions, I don't like roots.
Yes.
Time to change your major to business. No, because you've got that power of 1/3, you can't mash it in with the power of 1/3. Because the power of 1/3 can't be split.
Even if I make it to a power of one, like something like 36.
Because essentially you're trying to split it. So you should be getting, here is your radius for your disk. If you wanted to draw your disk, it's, you know, something like that. So the area of your disk is pi times r squared. The radius is the function. So when we square it, we're going to have x over x squared plus 1 to the 2/3. Does everyone agree with that? So when we square this numerator, just get an x. In the denominator, that's x squared plus 1 to the 1/3. And when you square 1/3, you get 2/3. So that is the area of the disk at x. The volume will be the limit as b goes to infinity, integral 0 to b of that. So we integrate area to get volume. And what technique of integration? Sub? Yeah. And where are we going to let u be? X squared plus 1, because the derivative of x squared plus 1 is 2x, and we can make the numerator 2x. So whatever you let u equal, its derivative must match. Or we can divide by 2. All right. So we're going to let u be x squared plus 1. U is x squared plus 1. Du will be 2x dx. So du over 2 will be x dx.
Can we just take that 1/2 and move it all the way to the front?
We can move it all the way to the front. Yep. So the pi we're going to move to the front. The 2 in the denominator we're going to move to the front. So we'll make that a pi divided by 2. Then we have limit. And let's see, what do we have in here? So we're converting to u, so these limits are no longer, the x limits are no longer applicable. We'll go back to x at the end. So here, isn't it going to be just u to the negative 2/3?
Yeah.
du. Because x dx, it turns into du over 2. The over 2 comes out in front. So then we can do this integration. We'll get u to the 1/3 divided by 1/3. Placeholder limits. Convert back. Go back to x. When we go back to x, we said u was going to be x squared plus 1. So we're going to have x squared plus 1 to the 1/3. Original limits, 0 and b. So we get 3 pi divided by 2 limit as b goes to infinity. All right, there's where we're at.
Infinity.
Infinity. As b goes to infinity, b squared plus 1 goes to infinity. And b squared plus 1 to the 1/3, that's the bird wing in quadrant 1. That's also going to infinity. So that's all going to infinity. And infinity minus 1 goes to infinity. And infinity times 3 pi over 2 goes to infinity. So this is infinite. So we have a divergent integral. Which is what we suspected by looking at the graph, because that graph didn't look like it went to x very quickly.
So we get the graph from the exam.
If it's a function like that, I would give it to you. Yeah. If it's a function like 1 over x or 1 over x squared, no. So if it's a function that's a little abstract, then yes. All right, we ready to go vertical? No. We've done all these horizontal tails. Time to go vertical. Here we go. Hold on tight. All right, so vertical is a little bit harder because you don't see infinity in the limits. Let me just jump to the next slide for a moment. So when we look here, here's a picture of 1 over x squared. If we integrate from 0 to 1, we have this vertical tail, and nowhere in the integral do you see infinity. You don't notice that it's an improper integral by just looking into the limits. Whereas a horizontal tail, yeah, it's obvious because you have the infinity right in the limit. But here, what is the problem? How do you think we could tell that this is an improper integral? 1 over 0, exactly. So in Calc 1, you learn for a definite integral, the integrand has to be continuous on your interval. But this function is not continuous on the interval because it's undefined at 0. So that tells us there's a vertical asymptote at 0, which means there's going to be this vertical tail. So that's going to be kind of where we're thinking about. Let's look at this page first on how to set it up. So when we look here, you can't tell right away that it's improper, but you can tell if you look inside at your limits of integration. If one of them gives you something undefined, then you know it's going to be improper.
Isn't that when we multiplied it by a negative and changed the limits of integration?
Well, we can't multiply by a negative. It's still, if you have division by 0 and you multiply by a negative, you still have division by 0.
Okay.
So if the limit of integration, so in Calc 1, they just always gave you limits that the function was continuous on. So here, we just have to look carefully and make sure. So what's happening, if we look at this vertical tail here, we're going to do the same type of thing we did before. We're going to say, oh, well, let's just approach the bad spot. So here, we're good all the way to the B, but it's this direction. So this right in here is definite. But then we're going to let C creep over towards that asymptote. And so this is going to be a one-sided limit. So the limit as C approaches A from the right-hand side. So it's got to be a one-sided limit. Two-sided limit means that you're approaching A from either side, or both sides simultaneously. But we want to approach A only from the right. We're not going to approach it from the left. Now, if we had a setup like this, where the asymptote is to the right, same idea. We've got our rectangles over here that are totally fine. We've got all these. That's our definite integral. And then we're going to approach B from the left side. So if our asymptote is on the right edge, then we're approaching from the left. If the asymptote's on the left, we're approaching from the right. And very similar to the double tail, if you have the asymptote in the middle, then you have to treat it as two separate improper integrals and add them together. And the only way both the cumulative area is finite is if both are finite. If one is infinite, then the whole thing is infinite. All right, so let's try one of these vertically unbounded regions. Vertically unbounded. Now, one thing you are going to notice is that if you were to look at these reciprocals of x, the faster it approaches the x-axis, the less fast it's going to approach the y-axis. So you're going to have this whack-a-mole type of thing. If you whack it down here and it's getting closer to the x-axis, it's going to be pulling off the y-axis. And vice versa, if you push it to the y-axis fast, it's going to be peeling off the x-axis. So it's only going to converge on one side. One side's going to converge, one side will diverge. There's one exception to that, which we'll talk about. But in general, if it converges here, it's going to diverge there. If it converges here, it's going to diverge there. And we'll look at a graph in a minute. So let's first show, we already did this one, and we found that this one was equal to, what was this one, 1 cubic unit? Or 1 square unit, I think, was the first example we did. Was it a 1? No, it was 1. Okay, so that one is finite. Let's show that this one is not finite. So here we know that we are going to have an improper integral because we have division by 0. So 0 is the bad endpoint. It's the endpoint we have to approach. So we're going to choose C, and it's going to approach 0 from which side? The right side. So if our interval is 0 to 1, we're approaching 0 from the right-hand side. So we're coming to 0 from the right. So then this is going to be integral of c to 1, x to the negative 2 dx. And this part is the same as the other problem. We still have the same antiderivative. This is going to be minus 1 divided by x, c to 1. So this will be the limit of minus 1 minus a minus is plus 1 over c. As c goes to 0 from the right. So we're not taking the limit as c goes to infinity, so don't just jump up and write, oh, negative 1. It's very tempting. This is as c goes to 0 from the right. So this right here is going to go to where?
Infinity.
Yeah, it's going to be positive infinity. Because the denominator is getting smaller and smaller, so in your mind, you're thinking as we approach 0, 1/10. You divide by 1/10, you get 10. You divide by 100th, you get 100. You divide by 1,000th, you get 1,000. So as this c is getting closer and closer to 0, closer and closer to 0 means the 10th, the 100th, the 1,000th, the 10,000th. But then you're reciprocating it, this thing is going to go to infinity. And infinity minus 1 is infinity. So this will diverge.
What do you mean by like then you reciprocate?
So when c is going to 0, the way that you should be imagining,
Like 1 over 1,000 and 1 over...
yeah. So there's 0, so let's suppose that this is 1/10. And then you're getting closer and closer. So then we say, okay, now we're going to get a little closer, 100th, and then 1,000th. Right, so this is what it means to get closer and closer to 0. And it's 1 over this number that's getting closer to 0. So 1 over 1/10 is 10. 1 over 100 is 100. 1 over 1,000 is 1,000. 1 over 10,000 is 10,000. So as we get closer and closer to 0, this is going bigger and bigger. It's getting closer. It's going towards infinity.
Oh, because then you have to add... Oh, I see.
Because the 1 is in the numerator. Right, so it's 1 divided by c. So these are the c's down here. And 1 divided by that's 10,000. Or if you want to think decimals, think 0.1. 0.1 goes into 1 10 times. Then think 0.01. That's going to go in 100. Then 0.001. That's going to go in 1,000.
That makes sense.
Yeah, so if you like decimals better, think decimals. If you do 1 divided by 0.00001, you're going to get a huge number. So that'll be divergent.
What about 1 over x?
1 over x, we'll get to 1 over x. 1 over x will diverge on both sides, we will see. Okay, yeah, 1 over x is the one exception. It diverges on both. So let's look at this one now. So in order for us to create a reciprocal function that gets tight to y, the exponent needs to be smaller than 1 in the denominator. All right, so the bigger than 1, the 1 over x squared, the 1 over x cubed, the 1 over x to the fourth, that's tight on x and loose on y. If we change and go the other direction and we make these exponents closer to 0, that will make the graph get closer to y and further from x. So let's check both of these. So here we recognize that we have an improper integral because we have division by 0. That tells us there's a vertical asymptote. So this is going to be the limit as c approaches 0 from the right. Because our interval is 0 to 1, 0 and 1. We're coming into the right to 0. Dustin?
Does it always have to have a 0 on the bottom of the intervals?
No. But usually it's very common because 1 over x, 1 over x squared, they all have the
It could
y-axis.
be whatever makes it vertical asymptote.
Yeah, whatever makes the denominator 0. So if we look at,
Okay, got you. I know what you're.
you know what, yeah, so if we look over here, the 0 is going to be at -3.
Got you.
Yeah, so it's whatever makes that denominator 0. Okay, so then we're going to have the integral from c up to 1, or over to 1. And we're going to put this in the numerator so that we can use the power rule. And let's just do this one parallel so you can kind of see the difference. So here we're going to let b go to infinity. And we're going to have the integral from 1 to b, same integrand though. So horizontal tail on the right, vertical tail on the left. Both will have the same antiderivative. X to the 3/4 multiplied by 4/3. C to 1. Same antiderivative. Different limits. Plug in limits of integration. And we can factor out the constant. Let's factor out the 4/3 here. It's easier to evaluate limits when there's less clutter. So limit of 1 to the 3/4, which is just 1, minus c to the 3/4. And then over here, same thing. Let's pull out the 4/3. And then we're going to have limit of b to the 3/4 minus 1. This limit is as c goes to 0 from the right, and this is as b goes to infinity. All right, the one on the right's easier. As b goes to infinity, b to the 3/4 goes to infinity. All right, that's the bird wing thing. So that's going to go to infinity. So the whole thing goes to infinity, so therefore we have diverges over here. Which is what we would expect looking at this picture. It's loose on x, it's tight on y, so that side's going to diverge. Now, let's see if we can evaluate this limit properly. Plugging in 0, we get 0 there. 1 minus 0 is 0, so this is our limit. So we have converge on this side. So this is going to converges to 4/3. That means that vertical tail has an area of 4/3 square units. Everyone okay with evaluating that limit with the c? If you plug in that limit value of 0 and you get a number, you're done. That means that the function is continuous at that value, and when the function is continuous at that value, the limit and the value are the same. For a continuous function, the limit and the value are the same. For a continuous function, the limit and the value are the same. Does that make sense to everybody? Like if you have a function, let's suppose you have x squared and you want the limit at 1. If you take the limit of x squared as x goes to 1, it's equal to 1 because this function is continuous here. And if it's continuous, the limit and the value are the same. Right? The value of the function right here is 1, and the limit of the function is 1. As you get closer and closer to 1, you're getting closer and closer to 1. So if the function is continuous, limit and value are the same. And so whenever we're evaluating a limit at a constant, we plug it in first, because if this function happens to be continuous at that value, the limit and the value are the same. So we do that.
One more point.
A continuous function, so this function right here, x squared, that's continuous. If a function is continuous, its limit and its value are the same. So in contrast, let's look at one that's not continuous. So if we have a function like this, let's suppose we have a hole right there, and we redefine the value of the function to be that. So that function is not continuous, so its value and its limit are not the same.
That makes sense.
Make sense? Yeah. So that's why we always plug in the number first to see. If we get a number, we're done.
How come in this one we did just plug in the 0, like just straight up, and then in the other one you like explained it like a little differently?
Because this is a limit at a constant. If you have a limit at a constant, you plug that constant in first. This is not a constant. So when we have a limit at infinity, we have to approach it differently. So when we have a limit at infinity, we're thinking what happens as this b gets larger and larger and larger and larger. Which the looking at the graph is kind of a visual way to do that. If we have a bird wing, if we are going to let the b's go to infinity, we're going this way, and then the y's are also going to infinity. So if you have a limit at infinity, it's just a different, you can't just plug in infinity. Although that's kind of what we think mentally. We think, oh yeah, if we plug in infinity, that means going out there forever, which means going up there forever.
What I meant like the previous vertical one where.
So the previous vertical one,
like
if we
1 over.
plugged in, we got something undefined.
Yeah.
Right? If you plug in 0, you get undefined. Which you can interpret as infinite if you, right? You could interpret 1 divided by 0 as infinity. You could interpret it that way. But what we really shouldn't be thinking of 1 over 0 as infinity. We want to, there's no guarantee that we're going to get positive infinity unless we do a little bit of analysis. Like if this was a two-sided limit, is it clear that, let me just remind you of one thing back in Calc 1. If you have this function, 1 over x, the limit at 0, the two-sided limit, is undefined. That's all you can say for the two-sided limit. That's it. You cannot say anything more precise. When you say that a limit is infinity, it means the limit doesn't exist, but it tells you how it doesn't exist. Here, we cannot do that. But if we change this and we say, what is the limit of y as x goes to 0 from the right, what would we say? Positive infinity. And if we say, what's the limit of y as x goes to 0 from the left, what would we say? Negative infinity. So both of these limits right here do not exist. And actually, that's usually what we write. We usually don't write undefined. Usually we write D and E. Does not exist. So these limits also do not exist, but you can be more precise. This says that as you're coming in from the right, the y values are going up without a bound. Here, as you're coming into 0 from the left, the y values are going down without a bound. Even though it is correct, if you wrote D and E here, it is correct, but it's not as correct as it could be, because you could be a little more descriptive. So So it's not just as simple as saying, oh, 1 over 0 is infinity. Because you have to think about what side you're coming into 0 from. But, all right, so let's carry on. So let's do one with a double vertical. Oh no, this one, we're just going to do one side. Let's not do a double. Okay, so when we look here, we notice that we have an asymptote at -3. Yeah, we do, right there. I see it. So -3 gives us a vertical asymptote right here. So what we're doing is picking a c value to the right of it, and our integral ends at 1. So this region here, we're thinking of this, thinking about all these rectangles all the way up to here. That part is definite. So we're going to integrate from c over to 1. And that's going to give us a function of c, and then we're going to take the limit as c goes to -3 from the right side. Now we're going to approach -3 from the right. So this will be limit as c approaches -3 from the right. C to 1. And again, we'll just pop this into the numerator. So we have that definite integral, the definite integral from c to 1. That we can integrate. We can integrate a definite integral. And what technique of integration are we going to use here? Power rule. And there's going to be a little reverse chain rule. Power rule and RCR. So we're going to get a 2x plus 6 raised to the 1/3. Dividing by 1/3 is multiplying by 3. So that's the power rule part. And then the RCR part, we are going to
Divide by 2.
divide by 2. You guys are flying. And then our limits of integration are c to 1. So let's factor out the 3/2 because it's just a little easier to clean it up. A little easier to evaluate the limit when it's cleaned up and you don't have extra constants in there. Don't have to. Of course you don't have to. So you're going to have 8 to the 1/3 minus 2c plus 6 to the 1/3. Before we even think about evaluating this limit, what is the power on the x in the denominator?
1.
2/3.
2/3 is the overall power on the x in the denominator. So are we expecting a vertical tail to be finite or to be infinite? Finite. If we have a fractional exponent, we're going to have convergence vertically and divergence horizontally. If you have a power of x in the denominator that's bigger than 1, you have convergence horizontal and divergence vertically. So we are expecting to get convergence because that power is less than 1. Okay, let's see if we do. And you can look at the graph a little bit. You can see that it's tighter on this vertical asymptote than it is on x. You can see it's a little closer, a little tighter. All right, so let's see what we get here. So this limit is as c goes to -3 from the right. So obviously the limit of the constant is itself. So that, and what is 8 to the 1/3? That's 2. Minus. So now we plug in the -3. That's the first thing we do. We plug it in because if that function over there is continuous at -3, its limit, its value are the same. So we plug in the -3. -3 times 2 is -6. -6 plus 6 is 0. So there is the area. because this business here is going to 0. Bless you.
And that means the entire area from -3 to infinity is 3.
No, because we're stopping at 1.
Oh, okay.
So it's -3 over to 1. This whole area in here is going to be 3. Yeah.
No.
Now, if you went out to infinity here, this tail is going to be infinite though,
Okay.
because we've got the whack-a-mole thing. Alex, do you?
The limit of a constant is what is it?
The limit of a constant is itself.
It's just itself.
It's just itself. So 8 to the 1/3, the third root of 8 is 2.
Yeah.
So limit of a constant is itself. All right. We're doing real math now.
You weren't before?
Point! Good point. Good point. Wait, what chapter are we in?
11, apparently.
Okay.
Oh.
So this little sleepy curve. We want to integrate that little sleepy curve from 1 to infinity and figure out if that area is finite. So let's think. If it was just 1 over x squared, we know it would be finite. This numerator is going to infinity very slowly. So the question is, does the x squared in the denominator go to infinity in the denominator? If that does the denominator go to infinity fast enough to offset this slowly growing natural log function? That's what we're finding out here. Now, if this numerator was a constant, or if it was arctangent, for sure we know it would converge. But this natural log function is going to infinity, so we're going to have this little wrestling match between the denominator going to infinity and the numerator going to infinity. Let's see who wins. We'll do the math to see which function dominates. So we're going to have limit as b goes to infinity, 1 to b, natural log of x over x squared dx. U substitution will not work. Is it obvious that U substitution will not work? Because the derivative of natural log of x is 1 over x, not 1 over x squared. So the derivative of natural log of x isn't present. All right, and if you let u be x squared, the derivative is 2x, and that's not present.
What if we multiply by
Integration by parts. We have a product of functions. Right, that's a product. Division is a product. It's natural log of x times 1 over x squared. So we're going to do integration by parts. So we're going to have u equals natural log of x. That's the natural choice. Because we don't know the antiderivative. Some of you might know by now, but so dv is going to be x to the minus 2 dx.
I thought U is what we wanted to shrink.
So there's two things. We do like to shrink u, and 1 over x squared is not going to be shrinking when you take its derivative. If it was just x squared, it would shrink. But 1 over x squared won't shrink. And moreover, the antiderivative for natural log of x is not like a simple known antiderivative. So du equals 1 over x dx. And when we integrate here, we get b equals -1 divided by x.
Isn't that just... No.
Okay, so let's see what we get. So we're going to have limit. So this integral is going to be rewritten as uv, ultraviolet voodoo, uv minus integral of v to u. uv is minus 1 over x times natural log of x. I guess we could just write that as natural log of x over x. So there's uv, and we've got this 1 to b here. So there's uv minus the integral of v du. V du is minus 1 over x squared. So that becomes plus 1 over x squared. And we will write 1 over x squared as x to the negative 2 because it's easier to integrate it that way. Everybody following that? So uv, that's our main diagonal right here. That main diagonal, negative 1 over x multiplied by natural log of x, and then minus the integral of v du, but v du is negative, so negative and negative is positive. And then x times x in the denominator is x squared down below, which is an x to the negative 2 up above. So that is integrable. That's where we say, hey, did this get easier? And we say, yeah. Yeah, that is easier. So let's not evaluate the limit yet. Let's just wait until we finish all this business. So the integral of x to the negative 2, once again, add 1 to the exponent, divide by the new exponent. So we get negative x to the negative 1. Negative x to the negative 1.
Wait, wouldn't the dv be x to negative 2? So in our
Here?
UdV, yeah. Well, in our UdV part,
Yep.
why is it just ln x over x? Like down the black writing.
This is u times v.
Oh, it's not u times dv.
It's no. The integration by parts. The ultraviolet voodoo part is uv minus integral of v du. So that's u times v.
All right.
That's all good.
So, is it going to be infinity?
I don't know. Let's find out.
Well, it's negative infinity.
Keep your hold on. Let's plug in our limits. Plug in the limits. So does everybody agree with that? Plugging in the upper and lower limits.
Yes.
Plug in the b, and you get this whole thing with the x's replaced by a b. And then remember, you're subtracting antiderivative at 1. So subtracting means adding. Subtracting means adding, in this case. And so then plugging in 1 here, natural log of 1 is 0. Plug in 1 here, we have a 1. And this limit is as b goes to infinity. Where do these two things, where does this one go? That definitely goes to 0.
So we have 0.
So,
I think it's negative infinity over infinity. Which one's bigger?
so in Calc 1, you learned a very important technique that we're going to see a fair amount in here, and that technique is L'Hopital's rule. L'Hopital's rule.
Take the derivative of both.
The hospital.
The hospital. Go to the hospital. If you have a headache, go to the hospital.
And whichever's bigger.
So let's think about L'Hopital's rule for a minute. So L'Hopital's rule says that if both the numerator and denominator are separate functions, if they both go to infinity, we take the derivative of both because the quotient of tangent lines should do the same thing as the quotient of functions. The quotient of functions, we have these two functions, and their quotient should do the same thing that their tangent lines quotient will do. So we're replacing the quotient of functions with the quotient of tangent lines. Right? If the tangent line is the best linear approximation, then the quotient of tangent lines should do what the quotient of functions does. Right? If we're going to approximate each function with its tangent line, the quotient of functions should be approximated with the quotient of tangent lines. So that's all L'Hopital's rule says. We just take the derivative of top and bottom. Simple. So the derivative of the top is 1 over b. And what's the derivative of the bottom with respect to b? 1. And then we still have that plus 1 lingering out there. Lingering.
That's negative 1 over b.
So that's going to be, if we want to rewrite it one more time, that's going to be negative 1b. And that'll be 1. So 1 over b is going to go to 0. So that, remember where we started. What were we finding? Oh yeah, the area of that little sleepy curve. So the area of that thing is 1. Another area that's 1.
So natural log beats x squared.
So does natural log beat x squared, or did x squared beat natural log? If natural log was going to go to infinity, right? So x squared is going to infinity fast enough to offset the natural log that's trying to make this diverge. So that the denominator is winning. Let's see. Is there any more math we can do? Oh, the summary. The summary. This is like perfect timing. Right.
It's like it was all planned.
All right.
We made it, you guys.
All right, so let's take a look at this little summary here. So this is, let's go down to the picture. You guys want pictures. So the black curve is 1 over x. The black curve, 1 over x, is going to have divergence in both the horizontal and vertical tails. 1 over x is bad on both sides. But if we look at the red curve, this is where we've bumped up the exponent just a little bit more than 1. And if you bump the exponent up a little more than 1 in the denominator, it's going to get close. It's going to close in on x faster, and it's going to pull away from y. So this will be horizontal convergence and vertical divergence. If the black one diverges already and you're even further away, then the red's going to diverge for sure. The blue, we're going to bump the exponent just a skosh below 1. So if you go a skosh below 1, it's going to pull it tighter to y and pull it away from x. We are going to have vertical convergence and horizontal divergence for the blue. Now, everyone always says, well, where are we going to use these improper integrals in the real world?
Never.
The coolest thing that you will do when you take differential equations is look at something called the Laplace transform.
Does that use everything?
The Laplace transform, the Laplace transform is an improper integral. And the Laplace integral is super cool because you know how we love taking derivatives?
Yes.
But if we have a function that doesn't have a derivative, like if you have a step function, right, there's a gap, it's discontinuous, you can't take the derivative. But if you Laplace it, it takes it from the t domain into the s domain. There you can do math in the Laplace domain and then invert it and get back to the t domain, and you can do math in the Laplace domain instead of in the t domain.
So it's another way of doing U substitution.
Yeah, it's U substitution on steroids. But you'll get to that when you get to, so improper integration is going to be very important to understand because it's going to come back. It's going to come back. All right, go shovel a driveway. Is it really snowing out there?
It stopped.
Did it stop?
Before class, yeah.